Welcome to the continuing videos in the linear algebra series. So in this video, we'll just talk about a few special types of matrices that haven't been covered in previous videos, or at least haven't been specifically defined in our previous videos. So all of these are going to be examples of square matrices. The first one being what is already shown here is the diagonal matrix. So the idea behind a diagonal matrix is more about what is not on the main diagonal than what is on the main diagonal. So the idea behind a diagonal matrix is that the entries on the main diagonal, the entries on the main diagonal can be anything. For example, 1, 2, 3, 4, but everything off that main diagonal is going to be zeros. So the main purpose behind a diagonal matrix is, if you got to this point here, you would have noticed that there are a few properties that don't hold. Specifically, AB equaling BA is certainly something that isn't true. And specifically, A squared wouldn't be something where you just squared every entry. That being said, the diagonal matrices are the exception to this rule, where we would be able to square a diagonal matrix simply by squaring all the entries, because, all the zeros going on there. So if we did just multiply it by itself, aka squaring this matrix, whenever you did do something that would be on the main diagonal, that'd be 1 times 1. Bunch of zeros and 2 times 2, a bunch of zeros and 3 times 3. But if you took any entry, let's say the first column or first row, third column, we just end up getting 0. 1 times 0 plus 0 times 3, which is 0. So everything off the main diagonal of the product would still be 0. And you'd get 1 squared, 2 squared, 3 squared, 4 squared. And everything off the main diagonal would be 0. And it doesn't just stop at 2. You'd get that whenever you have any diagonal matrix multiplied by any other diagonal matrix, you just end up multiplying those diagonal entries. And so diagonal matrices are nice because taking them to large powers, while incredibly awful when it comes to matrices in general, is very easy to do when it comes to diagonal matrices. So that's one of the nice things about diagonal matrices, but in terms of what they are, it's just a matrix whose only non-zero entries occur along the diagonal. Now, one thing to be careful about, just in terms of that definition, is that there's no rule that says that you have to be non-zero along the diagonal. So in this case right here, we still have a diagonal entry. So if there are non-zero entries, they occur along the main diagonal, but that doesn't mean you can't have zeros. So zeros are allowed on the main diagonal, they're just required off the main diagonal. So for example, any square zero matrix would be an example of a diagonal matrix. So that's what a diagonal matrix would be. They're very nice, very useful. For example, if we get them as part of a coefficient matrix in a reduced row echelon form, you can read off the answers right away. There's a lot of nice properties that come along with diagonal matrices. The second special type that show up from time to time is something called a triangular matrix. There's two types. There's the lower triangular, there's the upper triangular. So if we had a lower triangular matrix, that would mean that every entry above the main diagonal has to be 0. So for example, 1, 2, 3, 4, 5, 6, 0, 0, 0. This is an example of a lower triangular matrix because all of the non-zero entries, if any, occur on the lower triangle. Of course, they don't have to be. You can have zeros underneath. So for example, a diagonal matrix would be an example of a lower triangular matrix. and also an example of an upper triangular matrix, where the exact opposite, all the non-zero entries occur on or above the main diagonal, and everything below the main diagonal would have to be 0. So this is what a triangular matrix is. They aren't as nice as the diagonal matrix. They don't quite multiply quite as nicely as what a diagonal matrix would be. Just in practice, we can't always force things to be as nice as diagonals. So a lower and or upper triangular matrix is a, close second in terms of niceness when it comes to some of these properties. For example, an upper triangular matrix times another one is going to still be an upper triangular matrix, so you only have to worry about the entries above, as opposed to the entries below. So not as nice as a diagonal matrix, but still nice. There are some properties that we'll see later. Whenever you have a triangular matrix, there are certain things that we can find very easily, which for matrices in general can sometimes just be harder. The last type of matrix that we're going to be looking at here is something called a symmetric. A symmetric matrix. Now, a symmetric matrix doesn't have to be upper, it doesn't have to be lower, doesn't have to be diagonal, although a diagonal would be an example of a symmetric matrix, but it is kind of what you might think it is. So let's say we had a matrix right here. The idea is, if we think of the main diagonal as being a mirror, then what gets shown on the above, the upper triangle, so to speak, gets mirrored down to the lower triangle. In other words, since you had a 3 here, you have to get a 3 on that side. Similarly, a 4 here forces a 4 there. And a 5 here forces a 5 on the corresponding entry. In other words, the ij entry has to be equal to the ji entry. Now again, on the main diagonal, anything can happen. There's no corresponding matching entry on the main diagonal, but if you're off the main diagonal, they have to come in pairs. What you get for the 3s here, the 4s, and the 5s as well. So that's what a symmetric matrix is. So feel free to pause the video in just a second and see if you can fill in the following blanks. So a matrix A is called symmetric if blank is equal to A. So, hopefully you had a chance to pause the video and think, or maybe you figured it out without pausing the video. The idea, as kind of illustrated in here, is where if you switch the row and column, it stays the same. In other words, A transpose is equal to A. So, that's what it means for a matrix to be symmetric. In terms of a nice compact definition, but it kind of just means you have corresponding matching entries. The entry A13 matches with, the entry A13 matches the entry A31. And maybe you'll want to think about it its own and say, well, wait a second, I said every single property here had to do with square matrices, but my definition doesn't say anything about the matrix being square. So I'll let you think about why just this property being true forces the matrix to be square. And the idea is the sizes of the transpose wouldn't be equal to the size of A if it wasn't a square matrix. So even though it's not directly stated here that the matrix has to be square, it certainly is implied by the fact that this statement is true. All right, that's it for this video. See you in the next one.